Okay, so I want to start looking at our next section, our last section for this school year. It's the introduction to calculus topics, and this very first video, there's not a whole lot of notes for you to write down in your workbooks that you already have, but maybe on a scratch paper, kind of follow along, just to give you a background of what calculus is and how we're going to start. So I've given you a function on the screen here, and the function is a rational function, quadratic divided by linear. And what I want you to do is I want you to type this into your calculator, and you need to be really careful typing this in so that you make sure you have this entire expression in the numerator and this entire expression in the denominator. So I'm going to switch gears to an online graphing calculator. And again, maybe I can clear this out and redo it again. Use parentheses. It's x squared minus x minus 2. And then close your parentheses so you have that all in the numerator divided by x minus 2 in the denominator. Okay. Now, a lot of us maybe intuitively just go right to graph, but I don't want to go to graph. I actually want to go to the table, and I want to look at the table of values. And just so we're all kind of like on the the same page, if I go to table setup, right now it says, and I found that, by the way, table setup, right? It's like second, and then up here table setup. My table's starting at 2. And right now my change in table value is changing by 1. And if I just go right to my table, I can see that there's an error at 2, which shouldn't be a surprise because look at your function. You can't divide by 0. When x was 2, that put a 0 in the denominator, so no surprise. But I have an error. And I can scroll up and scroll down and maybe you've used really your table feature. But I look at my pattern here, like 0, 1, 2, error, 4, 5, 6. And I could make a guess that that error really should be 3, right? That's the number that's sort of missing in the sequence of y values. But the question is that a good guess? And are we close enough to 2 to really analyze this behavior? So what I'm going to do then is go back to my table setup and get closer. Let's still start at 2, but let's instead change by 0.1. Okay, so that delta table, again, means how much do you want to change it by? I only want to change it by 1/10. And again, don't go to graph, go to table. So there's our error, still at 2, right? Our error is still at 2, but notice that now we're within 1/10 of accuracy, and it still looks like that error should be 3. Like that 3 sort of fits the pattern. And in fact, we can get even closer. So I go to second table setup, and again, go back and start at 2 because if you toggled up or toggled down, you would have started a different spot and go let's go 0.01. All right, and we hit table. If you accidentally hit graph, that's okay. But again, we're getting, it's almost like we're zooming in, right? We're using a microscope to get closer and closer to the behavior of the function at 2. And like now to 1/100th of an accuracy, we look like it should be 3. And I mean, you can do this for however much you want to get confidence and like, yes, this pattern fits, and really that error, for some reason, it should behave like a 3, even though you can't divide by 0. So go back to that table. I'm pretty confident that this error should be 3. Like in terms of finding that missing number, right? Like it looks like the behavior of the y's is a value of 3. And in fact, that I did a couple screenshots earlier today, just saying, look at again, like it looks like it should be a 3. Here, it looks like it should be a 3. Here, it looks like it should be a 3. And the last screenshot actually is the graph. And this looks like a line. And it is a line. Well, it's almost a line, or actually it's less than a line. I mean, the behavior of this function is very linear, even though deceivingly it looks like it should be quadratic in the top and linear at the bottom, a rational function. But if you think back to the first semester, because what we see here, or we don't see, is there's actually a hole. There's a hole when x is 2. There's a hole, and that hole happens at 3. Now the hole is only undefined for that one instant. So we can't possibly see that with a graph. So the calculator sort of connects the dots and tries to guess what's happening, or like it's predicting this trend. So it's predicting a linear function that would have gone right through 2, 3. And so that's really where calculus, I guess, kind of starts, is this idea of like what's happening around 2, getting close to 2, and how close is close enough, as we start to analyze this function. And we want to maybe come up with a little bit more sophisticated way to talk about that. And so that's where we're going to introduce this notation and this idea of a limit. So this LIM that I have right here basically is the mathematical way to say we're going to look at the behavior of this function as we get really close to 2. As x gets close to 2, what's happening? And the thing is that I need to use this arrow to show that I'm approaching 2, because I can't ever let it equal 2. And if you haven't noticed, tried this yet, okay, so I'm kind of switching gears here, that if you actually do try to let x equal 2, and we put that in, well, obviously I'm getting 0 in the bottom, but then I put it up here, 2 squared is 4, minus 2 is another 0. And so we get 0 over 0. And again, last semester we learned, if you have 0 over 0, that means there's a hole in your function. And so it's still not defined, but this idea of approaching 2. Okay, and so I'll talk about that, and you'll learn a lot about that and say a lot of that next year. So you're approaching 2. So you're never going to equal 2. You're just going to get really close. And how close is close enough? Well, close enough until you can understand the behavior of what's really happening behind this 0 over 0. Because 0 over 0 is what we call an indeterminate number. Indeterminate number, or indeterminate form of a number. Okay, because we don't really know what's happening. It's not 0. Does not exist. It's not infinity. But what it is it's masking really the behavior of the function. And so you need to analyze that a little bit further. Okay, now another thing I want to show you on this idea of limits, again, that's not really in your notes, but just kind of watch and follow to just maybe get a good intuitive understanding of this idea of a limit. So if I look at this problem up here, it says I'm going to approach 1, get really close to 1. And so I can see 0, I can see 2, and 1 is hiding behind this yellow bar. So I don't really know what the behavior is. I don't know. I'm going to try to guess. I'm going to try to base it on evidence of what's happening close to 1. And so the thickness of this this kind of yellow that's kind of blocking my view, it doesn't tell me exactly what's happening, but I can kind of see a trend. I can kind of see it's heading towards the x-axis. I can kind of see that maybe the behavior of this function, aka the y value, might be 0. And this is our good friend, right? Our sine function. Look at that, how nice and balanced and aesthetically pleasing it is to have an amplitude of 3 and a period of 2, which means your frequency was pi to get that value. But let's say I want to get closer. So I said, okay, let me zoom in a bit to that area, or make that area smaller. So I've decreased the width. I've gotten a little bit closer to 1 on either side, and I'm looking at the behavior. What's happening with the y values? Are they approaching the same y value from both sides of this rectangle? And it looks like they are. It looks like they both are. And one thing you can't see, like I'm using my finger here, but you can't see that. But what I'm trying to do is show like the behaviors approach that way and approach that way. Are they meeting together? Okay, so let's see. Can we make this width a little bit smaller? And I know, right? This is great. I have so much free time. I can make rectangles that are infinitely smaller, right? So now again, what's happening to the graph? Are they getting closer and closer together? And I might say, yeah, I'm pretty confident that they looks like they're going to meet in the middle, but I might want to get more confident. So I narrow my view, and I can see a little bit more of the function. Are the y values getting closer? And then I can really narrow that in. I mean, again, I'm pretty confident this graph is approaching the same value. And then again, a little bit narrower, still pretty confident. A little bit narrower, still pretty confident. And then, oops, my bad. That kind of takes the It makes it very anticlimactic. If I grab that, there we go. Right there at 1, the function was approaching 0. So I had a lot of confidence that those y values were getting really, really close to that value. Now, I don't really care that the function value was equal to 0. All I care about as I get close to 1, what is the function values approaching? And so, oops, go to my pen. There it is. So I would say the limit value is 0, that the y values are getting closer and closer to 0. And again, this idea of approaching 1 as x gets close to 1, what's the behavior of the function? Okay, now, again, why not? Let's just double check to make sure this concept's sticking. I would read this problem, the limit as x approaches 1 of the function. So what I'm trying to find here is a y value. And it's a y value that's going to describe, let's pick another color here, the behavior. Let's see, does this show up nice? No, it does not. I want to try to find the behavior of the function. Behavior of function. And again, it's not when x equals 1, it's when x is getting close to 1. And so our job is to answer how close is close enough. So again, just like last time, right, we're removing these layers. And I'm looking at the behavior, as I approach from this side and this side, are they getting closer and closer together? And so then I remove this, and I can see, yes, it looks like the functions are getting closer, again, closer to that 0, and that's good. They're behaving the same way from both sides. It looks like they're approaching this value of 0. So I have a lot of confidence that I can say that this limit, just like the last example, that this limit was equal to 0. And even if I continue to remove this layer, and I see the blue, and it still is getting closer to 0. And I remove this yellow, and it looks like it's still getting closer to 0. And if I actually remove it all, I see there's a hole. Oops, right? I see there's a hole right there. And in that hole, it's not defined. It actually jumps up to here. So this is a really weird function because it's almost the sine graph. It's the sine graph for every point except for this one point. There's a hole at 1, 0, and up here instead there's a function value when x is 1. The function value is actually 2. Okay, but here's the thing. It doesn't matter. It doesn't matter what the function value is. What matters is, well, what should it have been? What do both sides get closer and closer and closer to? And in fact, this idea of sort of blocking out the behavior of what's really happening, that's actually a really smart thing to do because I don't want to be distracted by jumps or asymptotes or holes or things like that. What I want to know is, what is the evidence around 1? Not equal to 1, around 1, close to 1. What is the behavior close to 1? And when I answer that question, I'm answering the behavior as a y value. The behavior of all these y values as I get closer, 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 closer to 1, the behavior means that the y's are getting closer to 0. I don't care what happens at the point. I care what happens close to the point. And that's again, this definition here. I don't know if you wanted to write this down somewhere, but that's something I've had up for probably like 6 or 7 years, and I just like it. Okay, a limit describes the behavior of a function near a given point. And I've kind of highlighted a behavior that's a y value. I've highlighted the word near because I don't really care what's happening at the point. I want to know what's happening near the point. And to answer our question from the very beginning, where we were looking at that original function on our calculator, I would say that the limit as x approaches 2 of the function is equal to 3, because that was what the evidence showed. As I looked at the table, as I looked at the graph, all of the y values were approaching 3. And notice that this is a different question than saying, well, what was f of 2? What if I would have tried to directly plug in 2? I would have gotten 0 over 0, which does not exist. So the actual function value, which is what I just calculated here, the function value does not exist. Because there's a hole. So in calculus, we sort of come up with this idea of a limit to help us deal with functions that have holes in them, that have these discontinuities. So since I can't necessarily find the function at 2, but I can kind of figure out, well, what should have happened, right? Another good definition of a limit is, well, what should have happened? There shouldn't have been a hole there. The graph, you go back to that the image that let's see, I had here, and that image should not have had a hole. There's a hole. Oops, sorry, you can't see it. But like at 2, 3, technically there's a hole there, right? That shouldn't have happened. We should have been able to fill that hole. And in fact, if you were to have blocked out this, you would have had no reason to think that there was a hole there anyway. Because again, the behavior from the left and the behavior from the right are behaving the same way. The y values are converging onto this point 3. Now, one of the things that I really like as I kind of switch screens here, one of the things I really like as a teacher, and I talked about this all year, having like 1 foot in honors pre-calc land and 1 foot in calculus, is that right now we are like a week out of the AP exam. So my current calculus students, actually preparing for the AP exam. And it's out in my head, it's kind of like coming full circle because you guys are just embarking on your knowledge of calculus and they're getting ready to demonstrate what they've learned all year. So again, not a lot of notes to take, but I hope this was a really informative video. And I hope that, I hope that, that gives you a basis to start taking some more notes.